let me formulate two corollaries of the theorem on extension of homomorphisms. Corollary 1, that an algebraic closure of K is unique up to an isomorphism of K algebras. And corollary 2, that any algebraic extension of K embeds into the algebraic closure. So let me give you an example of extension of homomorphisms. So let's take K equal to Q, and let's fix an algebraic closure, Q bar. For instance, one can consider Q bar embedded in C, one often does that, as the set of algebraic numbers that is roots of polynomials with rational coefficients. And let us consider L, which is Q of the root of 2. One may see it like this, but it is better to say that L is the quotient of the polynomial ring by the ideal generated by x squared minus 2. So let alpha denote the class of x in L, and L has two embeddings in Q bar. Our alpha can go to the square root of 2. Let's call this phi 1, something which is identity on Q and sends alpha to the root of 2. And phi 2 sends alpha to minus square root of 2. Since alpha can go to both roots of the polynomial x squared minus 2. Now consider M, which is Q of the fourth root of 2, or better, Q of y over y to the power 4 minus 2, and call beta the class of y in M. Then this beta can go to any other root of the polynomial y to the power 4 minus 2. So M has 4 embeddings in Q bar. So beta can go to plus or minus fourth root of 2, or plus or minus I fourth root of 2. Those are roots of our polynomial y to the power 4 minus 2. Now, psi 1 sending beta to the fourth root of 2, and psi 2 sending beta to the minus fourth root of 2 extend phi 1. Indeed, M is an extension of L. M is L of y over y squared minus alpha, and so our psi extend something which sends alpha to the square root of 2. And psi 3 sending beta to minus fourth root of 2, and psi 4 sending beta to, minus I fourth root of 2 to plus I fourth root of 2. Extend phi 2. Indeed, phi 2 sends alpha to minus square root of 2, and here plus minus I fourth root of 2 are the roots, the square roots of the minus square root of 2. Over minus root of 2. Well, square roots, of course. Our next topic is finite fields. We have seen that a finite field is necessarily of characteristic P, where P is a prime number. So K is a finite extension of Fp, which is a finite dimensional vector space over Fp, if n is the degree of this extension, then the cardinality of K is p to the power n. One often denotes such a K as f p to the power n. So, of course, there are natural questions to ask, namely whether it exists and whether it is unique. We shall shortly prove a theorem which answers these questions, but let me first remark something about fields of characteristic P. If K is a field of characteristic P, then consider Fp from K to K, which sends x to x to the power P. This is a homomorphism of fields. Is a field homomorphism. That is, x plus y to the power p is equals to x to the power p plus y to the power p, and xy to the power p is equal to x to the power p, y to the power p. The second property is, of course, true in all fields, and the first is particular for characteristic p, because if you decompose this x plus y to the power p by the binomial formula, almost all coefficients will be divisible by p, so will vanish in a field of characteristic p. So one calls it Frobenius homomorphism. Frobenius homomorphism. In the same way, f p to the power n sending x to the power p to the power n is likewise a field homomorphism. This is just a power of our Frobenius. So let me formulate the first theorem about finite fields. So fix an algebraic closure. A splitting field of the polynomial x to the power p to the power n minus x. So the field generated by its roots in fp bar has p to the power n elements. Conversely, any field of p to the power n elements is a splitting field of x to the power p to the power n minus x. And moreover, there is a unique subextension of fp bar consisting of p to the power n elements.